There are those two numbskulls, Holmes and Watson, now still looking for the pirate's buried treasure. But I got here first, didn't I, my beauty? Pretty Molly, pretty Molly.
My word, Holmes, what a tropical paradise, real pirate country, eh? Yo-ho-ho, and a bottle of rum, what?
Thank you, Watson, but don't forget why we're here, to find the pirate's buried treasure.
Oh, yes, quite so. Have you got a clue, Holmes?
Not yet, but I'm keeping my eyes peeled.
Of course, they haven't got a clue. I'm the only one who has the clues. Directions for finding the buried treasure. Now, let me see. Ah, that's easy. So this is what I'll do. I'll go and dig up the treasure, and then I'll plant this bomb in its place. Meanwhile, I'll leave these directions behind for Holmes and Watson to find, and then, when they finally go to the treasure, it'll be gone, and kaboom, so will they. Cancelled out forever. Now, let me start piecing this out. 1, 2, 3.
What's this piece of parchment, Holmes? Directions for finding the buried treasure. Walk a certain number of paces east, and then a certain number of paces north. But how many paces? What numbers are we looking for?
Watson, look at the clues.
Yes. 3 times the first number increased by twice the second number equals 63. And twice the first number decreased by 3 times the second number equals 3. Oh, dear.
Quite simple, Watson. Follow me.
But wait, Holmes, there's something stuck to this parchment.
I might have known.
You don't mean Moriarty's up to his monkey business again?
Not monkeys, Watson. Parrots. This is a feather from Moriarty's parrot, Pretty Polly.
So the wretch got here first?
Yes, and knowing Moriarty, he plans not only to steal the treasure from under our noses, but to plant a bomb in its place.
Oh, dear, Holmes, what shall we do? Moriarty's gone too far this time.
Yes, indeed. Much too far.
Don't follow you, Holmes.
It's elementary, my dear Watson. Moriarty's nowhere near the treasure. He's gone quite far beyond it. I'll show you. By my calculations, to find the treasure, we go 15 paces east and 9 paces north. And here it is.
Wonderful, Holmes, and still no sign of Moriarty.
Of course not. He's way over there somewhere.
But how can you be so sure?
Here's another clue sitting right on your hat.
Pretty Molly, pretty Molly.
What? Polly the parrot?
No, Watson. Polynomials.
Welcome to the Power of Algebra, Program 6. In the last program, we looked at exponents, and we saw 2 rules of exponents. First rule, when you multiply powers, you add the exponents. A to the power of m times a to the power of n equals a to the power of m plus n. Second rule, when you divide powers, you subtract the exponents. A to the power of m divided by a to the power of n equals a to the power of m minus n. In this program, we're going to move up a level in harnessing the power of algebra. We're going to look at polynomials. Don't run away. See, so far in the series, we've looked at how to solve an equation by isolating one variable. Here's a simple example. 3 pairs for 27 cents. But what if you only wanted 1 pair? How much would that cost? Well, if x were the cost of 1 pair, we could say 3x equals 27. To get x alone on one side of the equation, we divide both sides by 3. So x equals 9. So 1 pair costs 9 cents. That's easy because there's only 1 variable, 1 unknown. What if you saw a sign like this? 4 apples and 3 oranges for 68 cents. You only want 1 apple and 1 orange. How much do they cost each? Now we have 2 variables, 2 unknowns. If X is the price of one apple and Y is the price of one orange, then we could say 4x plus 3y equals 68. How do you solve an equation like that? Well, there are several possible ways, but one way you can't solve it is to take 4x and add it to 3y and come up with 7 something. Why not? Well, you can't add x and y together any more than you can add apples and oranges together. X and y are unlike terms. Same as x squared, and the number 3 are also unlike terms. You can only deal with unlike terms separately. X plus y is x plus y. You can't put it any simpler than that. The same goes for x minus y. These are both groups of unlike terms linked together by a plus sign or a minus sign. You could think of them as multi-terms, and that's just what they're called in algebra. Only we use another word for multi, poly, plus the Latin word for term or name, which is nomens. That gives us polynomials. X plus y and x minus y are both polynomials. So is x minus y plus 2, or 2x plus 3y minus 4. Groups of 2 unlike terms are called binomials, and groups of 3 unlike terms, trinomials. So you can actually have 3 kinds of polynomials: monomials, binomials, and trinomials. You can think of monomials, a single term, as being sort of like a monocle, glasses with a single lens. You can think of a binomial as being like a bicycle, a two-wheeler. That makes a trinomial a tricycle. But the general label for all these terms is still polynomials, groups of unlike terms linked together by a plus sign or a minus sign. Now, back to the equation about apples and oranges. How do you find the values of these 2 variables, x and y? Well, first of all, 4x plus 3y is a group of unlike terms, a polynomial, or to be more precise, a binomial. You can't lump the x's and y's together. You have to deal with them separately. So how do we get the x's and y's on their own? Well, we have to find out some more information about x and y. Suppose there's another sign. That tells us 3 oranges cost 31 cents less than 5 apples. In other words, the difference between 5 apples and 3 oranges is 31 cents. 5x minus 3y equals 31. Now we have 2 equations, and that's the key. You have to have 2 equations to solve for 2 variables. The 2 equations are 4x plus 3y equals 68, and 5x minus 3y equals 31. So, how does this help us to isolate either the x's or the y's? Well, one of the easiest ways of doing that is to either add or subtract the 2 equations. So we line up the 2 equations, just as we would any string of numbers we wanted to add or subtract. But remember, we're dealing with polynomials here, and we have to make sure the like terms are in the same columns, with the x's over the x's and the y's over the y's. Now, do we add or subtract? In this case, if we add the 2 equations, then the y's will disappear, because 3y added to negative 3y is 0. So let's do it. 4x plus 5x equals 9x. 3y minus 3y equals 0. And 68 plus 31 equals 99. Now we can divide both sides by 9 to get x equals 11. So we know the value of x. And we can substitute that number for x in the original equation to find out what y stands for. 4x plus 3y equals 68 becomes 4 times 11, or 44, plus 3y equals 68. Now, subtract 44 from both sides to get 3y equals 24. Finally, divide both sides by 3. Y equals 8. So, x equals 11 and y equals 8. That is to say, the price of a single apple is 11 cents and a single orange is 8 cents. We can check this out by looking at the original sign. Substituting 11 for apples and 8 for oranges. 4 times 11 is 44, and 3 times 8 is 24. 44 and 24 are 68. It works. We've solved an equation involving two variables, our first polynomial equation. If only Moriarty had known how to do this, he would have not only been able to find the buried treasure, but he would have been able to cancel out Holmes and Watson as well.
Polynomials, you say, Holmes? Groups of unlike terms joined by plus or minus signs?
The very same.
But what's that got to do with Moriarty not being able to find where the treasure was buried? It's a mystery to me.
It's not one mystery, my dear Watson. It's two mysteries.
You mean two unknowns, of course. Two numbers we have to find. Two unlike terms. By George, we're dealing with polynomials. Now I understand.
Brilliant, Watson. And in this case, you also have two equations. 3x plus 2y equals 63.
And 2x minus 3y equals 3.
Now, all we have to do to solve the two equations is to eliminate either the x's or the y's by adding or subtracting the equations and multiples of the equations.
But how is that possible? The numbers of the x's aren't the same, and the numbers of the y's aren't the same.
Well, make them the same, Watson.
How do I do that?
Well, for example, to make the numbers in front of the y's the same, you simply multiply the first equation by 3 to give you 6y, and the second equation by 2 to give you negative 6y.
Oh, right-ho, Holmes. So that gives us 9x plus 6y equals 189. And 4x minus 6y equals 6.
Now, when you add the two equations, you'll be able to eliminate the y's.
Yes, 9x plus 4x is 13x. 6y minus 6y equals 0, so we've got rid of the y's, and 189 plus 6 is 195. Now we divide both sides by 13, so that x equals 15.
Then to find the value of y, we substitute 15 for x in the first equation. 3 times 15, or 45, plus 2y equals 63.
Subtract 45 from both sides to get 2y equals 18, so y equals 9. So to find the treasure, we take 15 paces east and 9 paces north. But that's exactly what you calculated.
Naturally, old chap.
But why did Moriarty get this wrong?
I told you, Watson, because he doesn't understand polynomials. Unlike us.
Oh, I get it, Holmes. Unlike us, unlike terms. He tried to add unlike terms.
Precisely, Watson. First of all, I'm sure Moriarty didn't line up the equations properly. And then, because he's so fond of cancelling people out, he no doubt tried to cancel out the 3's and the 2's and added 63 to 3, leaving him with x plus y equals 66. He then probably assumed that both x and y stood for half of 66, which is 33.
Oh, so you think Moriarty went 33 paces east and 33 paces north, huh? Let's go back to our starting point and pace it out to see whether you're right. 31, 32, 33. There we are. We've come exactly 33 paces east and 33 paces north.
Look down at your feet, Watson.
Good grief. Moriarty's been digging everywhere in the vain hope of finding the treasure. And all because no one ever taught him about polynomials.
Well, at least he's been taught one lesson. Not to try and monkey with Sherlock Holmes.